Good morning, students. In the last class, we discussed about the refraction by lens, that is lens maker's formula and lens formula. So today we continue the topic, that is combination of thin lens in contact. Combination of thin lens in contact. So consider two thin lenses. Consider two thin lenses of focal length f1 and another lens, that is B, with focal length f2. So we considered two thin lenses of focal length f1. The first lens we call as A lens and second lens have focal length f2. That lens we call as lens B. So this one is the principal axis. So consider an object placed behind the focus of the first lens. So here somewhere is focus of the first lens, that is lens A. I am considering the object is behind the focus somewhere here. The rays emanating from the object like this. After refraction through the first lens, the image will form at the refracted ray meets the principal axis at I1 like this. The rays which are coming from the object strikes the lens A. After refraction, the refracted rays meets the principal axis at I1. So I1 is the image formed by the object A by the lens A. So I1 is the image of an object O that is formed by lens A. So this one is the image I1 and here is the object. So if we taken here, so the object distance is u and the image distance is, so here the image we taken as I1, then image distance we taken as V1. So if we write the lens formula for the image formation by the lens A, that is the image formed by the lens A. So we can write by using the lens formula, that is 1 by V1 minus 1 by U, that is equals to 1 by F1, where F1 is the focal length of the lens A. So next here we are considering these two lenses are very thin, then the image I1 acts as a virtual object for the lens B. So this image I1 acts as a virtual object. So this is the image of the first lens. So this image acts as a virtual object for the second lens, that is for second lens. Then the real image is formed at somewhere here, that is I. So that is the distance V. Here these two lenses are in contact, that's why its optic center are also coincide, that is coincide each other. That point we call as point P, optic point P. From P the image is formed at V. So this image is the real image. Here the I1 is the virtual object for the lens B. So next the image formed by the lens B, the image formed by the lens B, that is this one is the image distance 1 divided by V minus 1 divided by, this is the object distance V1 for the lens B. that is minus 1 by V1 that is equals to 1 divided by F2, where F2 is the focal length of the lens B. This is equation 1 and this is equation 2. So adding equation 1 and 2, here it is positive of 1 by V1 and here it is negative of 1 by V1. So these two terms are cancels each other. Then we write the final equation. Write 1 by V1 minus 1 by U plus 1 by V minus 1 by V1 that is equals to 1 by F1 plus 1 by F2. So this term gets cancelled. So the remaining is 1 by V minus 1 by U that is equals to 1 by F1 plus 1 by F2. We get the final equation like this. This is the combination of two thin lenses. This system is the combination of two thin lenses, that is lens A and lens B. If we consider this system is equal to the single system, that is for single lens of focal length F. So this system of two lenses is equal to the single lens system. Then here is the object and here is the image type. So this is the object distance and this is the image distance V. So this lens has focal length F. So the system of two lenses is equals to the system of single lens, that is equivalent lens. Then if we write the lens formula here, we get 1 by V minus 1 by U that is equals to 1 by F. So this system is equals to the single lens system. So we can replace this term, that is 1 by V minus 1 by U can be written as 1 by F, that is equivalent focal length. 1 by F that is equals to 1 by F1 plus 1 by F2. So this is the final equation. When two thin lenses are kept in contact, then we get the resultant equivalent focal length 1 by F that is equals to 1 by F1 plus 1 by F2. If we write this in terms of power, if we write the same equation in terms of power, we know that power P is equals to 1 divided by F. So this becomes 1 divided by F becomes P. So here 1 divided by F1 represents power of first lens, that is lens A, and power of lens B. So the same relation can be written in terms of power. So this system is same for, we consider for any number of systems. If we consider the system has several n number of lenses that are kept in contact to one another, then we can write if lens has n number of focal length F1, F2, F3 up to Fn, then effective focal length can written as 1 by F is equals to 1 by F1 plus 1 by F2 plus 1 by F3 up to 1 by F1. So this relation is valid for any number of thin lenses kept in contact. For n number of lenses which are kept in contact, we can write the relation 1 by F is equals to 1 by F1 plus 1 by F2 plus 1 by F3 up to n number of lenses. If we write the same relation in terms of power, we can write P is equals to P1 plus P2 plus P3 up to Pn. Here, the combination of lenses may be either of both have the same lenses, that is, here we are considering both the lenses as convex lens. If we can combine convex and concave, either convex convex or concave concave, we can kept contact any of these lenses in combination in any number. So if we consider here one concave and that is one convex and one concave, here is it. One lens is convex and another lens is concave, then here the power becomes P is equals to P1 positive for the convex lens, and for concave it becomes minus P2. So the total power, the net power is equals to the algebraic sum of the individual powers. So this is about the combination of thin lenses in contact. If we write the magnification for thin lenses in contact, M1 is the magnification of the first lens and M2 is the magnification of the second lens, then the total magnification M can written as the product of magnification M1 and M2. So M1 is the magnification of the first lens, that is the individual lens. So the net magnification or total magnification is the product of magnification of the individual lenses. So these are the three important points. So this is about the combination of thin lenses which are kept in contact. So this combination of thin lenses used in cameras, microscope, telescope and other optical instruments. So this arrangement, combination of thin lenses arrangement used in cameras and microscopes, telescopes and other optical instruments. So this is the important derivation. In main exams they asked for 5 marks. They asked the derive the relation between the focal lengths when two lenses are kept in contact. So this is about the combination of thin lenses in contact. If we solve few problems on this topic, so the first problem on this topic is find the position of the image form of the image formed by the lens combination given in the figure. So here is given one convex lens of focal length f is equals to plus 10 and one concave lens of focal length -10 and another one convex lens of focal length plus 30 centimeter. So the object is here, that is object O, that is placed at 30 centimeter from the first lens. Then the gap between the first and second lens is 5 centimeter, and to the second and third is 10 centimeter. So in the given question, we have to find the position of the image formed by the combination of three lenses. Here we observe here there is no lenses in contact. Here we have three lenses, all the three lenses which are not in contact. So that's why we can't use the formula 1 by f is equals to 1 by f1 plus 1 by f2 plus 1 by f3. These three lenses are separated by distance. So the distance between the first lens and to the second lens is 5 centimeter, and to the second and to the third one is 10 centimeter. So how we solve this problem? How we obtain the image of this object? So by step we can find the image of the object. So first we have to find out the image of the first lens. So we have to find the image of the first lens. We have the lens formula 1 by v minus 1 by u, that is equals to 1 by f. So we know the object distance, that is 30, and we have the focal length f, that is 10. So here we can substitute 1 by v minus 1 by minus 30, that is equals to 1 by 10. So 1 by v minus into minus plus, if we shift to RHS, it becomes minus 1 by 10 minus 1 by 30. So if we take LCM here, that is 30 minus 10, this divided by 300, that is equals to 20 by 300, that is 1 by v. 2 ones are 2, 15 are. So the value of v is 15 centimeter. So the image is formed that is equals to 20 by 300, that is equals to 1 by 15. So the value of v is equals to 15 centimeter. So the image of an object is formed at somewhere here. At this point we get the image. So here is the image. So this image is formed from, this is 15 centimeter, that is v. So this 15 centimeter, here is the image. This image acts as a virtual object for the second lens. So this image acts as the virtual object. So then here the object distance becomes, from here to here it is 5 centimeter, from here to the image is 15 centimeter, then the image distance, that is from the image to the lens, that is 15 minus 5, that is equals to 10 centimeter. So this 10 centimeter the distance acts as the object distance to the second focal length. So in the next step, we got the image from the first lens, that is at 15 centimeter from the first lens. So this image acts as the virtual object for the second lens. It is at a distance 10 centimeter from the second lens. If we apply the lens formula for second lens, here it is the for first lens, here it is for second lens, 1 by V minus 1 by U, that is equals to 1 by F. So here we don't know the image distance, we know the object distance, that is virtual object distance, that is at 10 centimeter, 1 by 10. They given the focal length of the second lens, that is 1 by minus 10. If we shift the minus 1 by 10 to the RHS, it becomes plus, that is 1 by V is equals to 1 by 10 minus 1 by 10. So 1 by V is equals to 0. Then V is equals to 1 by 0. That becomes the infinity. So the image formed by the second focal length is at infinite. So this infinite distance acts as the object for the third lens. So this infinite distance acts as object for, so that is object is placed at somewhere here. That is at infinite distance to the left of the second convex lens. So if we consider this one is the infinite distance, somewhere here the image is formed. So this image acts as the, that is this image acts as the object for the third lens. Then the object distance becomes infinity. Next we have to find the for third lens. For third lens, that is focal length is plus 30 centimeter. If we apply the lens formula, 1 by V minus 1 by U, that is equals to 1 by F. So here the object distance is at infinity, 1 by V minus 1 by infinity, that is equals to 1 by 30. So 1 by infinity is 0, then 1 by V is equals to 1 by 30, then V is equals to 30 centimeter. So the image is formed 30 centimeter from the third lens. So this is the solution for the given problem. So in step by step we can solve the solution to find the image of the object which is placed at 30 centimeter from the first focal length, that is first lens. From the convex lens, the object is at 30 centimeter. The image is formed at 30 centimeter from the third lens, that is F is equals to 30 centimeter. Otherwise, we can directly say that the object is at infinite distance, then the image is formed at the focus of the lens. Then we given that focus point is, the focal length is 30 centimeter, then the image distance is equals to 30 centimeter. Next problem. So next second problem. An object of size 3 centimeter is placed 14 centimeter in front of a concave lens, in front of a concave lens of focal length 21 centimeter. Describe the image. Describe the image produced by the lens. Describe the image produced by the lens. Full stop. Next, what happens if the object is moved further away from the lens? So in the given question, the given an object of size, that is height of the object is 3 centimeter, which is placed 4 centimeter in front of the concave lens. Here the given lens is concave lens having the focal length 21 centimeter. So next, describe the image produced by the lens. Next, what happens if the object is moved further away from the lens? So consider one concave lens. So this is one concave lens. They given somewhere here height of the object is 3 centimeter, placed 14 centimeter from here to here. The object distance u is 14 centimeter, and the focal length here is somewhere the focus. So here the focal length is f is equals to 21 centimeter. So describe the image formed by the lens. So here we have to find the image distance and also the image size. We know the lens formula, that is 1 by v minus 1 by u, that is equals to 1 by f. So we know the value of u and also we know the value of f. We can simplify by substituting the values of u and f. We get, that is 1 by v minus, so minus 14, that is equals to concave length, the focal length is minus 21. So if we rearrange 1 by v, this becomes plus. If we shift to RHS, then it becomes 1 by 14 minus 1 by 21. If we take the LCM and simplify, so if we take the LCM means 14, 21, 7 2 the 7 3 is 42, then 14, this becomes 3, and minus 21, this becomes 2, that is 1 by 42. So image distance V is equals to 42 centimeter. So this gives the image distance. Next, we have to find the magnification formula. By using magnification, m is equals to height of the image to the height of the object, that is equals to b divided by u. For concave lens, m is positive, that is hi is equals to b by u into h naught. So the value of v is 42, the value of u is 40 into height of the object is 3. Then if we simplify here, 2 7s are 14, so 6 centimeter. So height of the image is 6 centimeter. So this is the image formed by the object. So if what happen if the object is further moved from the lens? So if the object is further moved from the lens, the image is moved towards the focus and gets diminished. If the object is further moved or further away from the lens in this direction, the image is formed somewhere here, it will move to the focus and gets diminished. So this is the solution for the second question. So next, third one, two lenses of focal length, two lenses of focal length 0.2 meter and 0.3 meter are kept in contact. Find the focal length of the combination. Find the focal length of the combination. Calculate the power of two lenses. Calculate the power of two lenses and combination. So in the question they given two lenses of focal length 0.2 meter and 0.3 meter are kept in contact. Find the focal length of the combination of two lenses and calculate the power of two lenses and combination. So the given is f1 is equals to 0.2 meter, f2 is equals to 0.3 meter, which are kept in contact. To find, so what we are going to find here is the focal length of the combination, that is f, and power of individual lenses p1, p2, and the combination of the power, that is p. So we know the formula for two lenses kept in contact. The effective focal length 1 by f is equals to 1 by f1 plus 1 by f2. So we know the values of f1 and f2. So the value of f1 is 0.2 plus the value of f2 is 0.3. If we shift the digit in the numerator, it becomes 10 divided by 2 plus it becomes 10 divided by 3. So here it is 2 ones are, becomes further complicated. If we take the LCM here, that is 10 divided by 2 plus 10 divided by 3, it becomes 30 plus 20 divided by 6, that is 1 by f. So f is equals to 6 divided by 30 plus 20, that is equals to 50. So 2 3s are 2 2s are 2 5s are 3 divided by 25. If we simplify 3 divided by 25, we get the final focal length is 0.12 meter. So this is the F final focal length. We get the answer is 0.12 meter. Next, we have to find the power of individual. So P1 is equals to 1 divided by F1. So here it is, P1 is equals to 1 divided by F1, that is equals to 1 divided by 0.2, that is 10 divided by 2, it is 5 diopter, 5D. So the power of first lens is 5D. Next, similarly, power of second, 1 divided by F2, that is 1 divided by 0.3, it is 10 divided by 3, it becomes 3 3s are 9, that is 3.33 diopter. So P2 is equals to 3.33 diopter. Next, the net power. The net power of the combination of two lenses, that is P is equals to P1 plus P2, that is 5 plus 3.33, that is equals to 8.33 diopter. So this is the net power. So here we can write here 8.33 diopter. So this is the, once they ask this question for 5 marks in annual exam. By using the formula 1 by f is equals to 1 by f1 plus 1 by f2, we can calculate the effective focal length, and by using the relation between the power and root to the focal length, we can calculate the individual powers of the lens, and then we can add, we get the net power of the combination of lenses. In the next class, we will discuss about refraction through prism. Refraction through prism, and few problems based on the topic. Thank you.